Okay, so let's start with the second part of like we are in the initial introduction part of Walther. We'll continue with chapter one and try to end chapter one in this video. So, on the contrary, it is undeniable that conservation of our quality of life and development for the major part of humans who still lack the most basic necessities of for a life of dignity require both mineral raw materials and an intact environment. So we need raw materials, like mineral raw materials and an intact environment. Mining without an impact on the environment is impossible. But the industry strives to minimize negative effects and to improve the welfare of affected communities, which is known as green mining. Some mining operations create an enriched landscape of constructed ecosystems which provide humans with a variety of services. Example, food, flood, erosion control, areas of recreation, aesthetics, and clean water. So, some mining operations create an enriched landscape of constructed ecosystems, which provide humans with a variety of services. Hmm. Examples include lignite and clay pits, which bequeath beautiful new lakes. Okay, after after having the pit and lignite and clay pit clear, we get the beautiful lakes. So hard rock mines and quarries may grow into rare islands of nature in a set of human occupation. Many of these sites support rare and threatened species from archaea and bacteria to plants and animals, helping to preserve biodiversity. Reversing mineral extraction, mines also have an extremely important role as deep disposal sites for the safe storage of society's unavoidable toxic and radioactive waste. Chemically dangerous waste is usually stored in work sections of suitable underground mines. Okay, so where are if this is very important, chemically dangerous, so all the radioactive waste, so the chemically dangerous wastes, they are stored in the underground mines. For highly toxic and radioactive waste, the construction of dedicated underground disposal mines is the best solution for protecting the biosphere. Underground disposal takes lessons from nature that preserve high concentrations of hazardous soil, solid and gaseous substances in the form of mineral deposits over many millions of years. Example, sulfide metal ore, natural gas, uranium, and even the remains of natural nuclear reactors. The World Commission on Environment and Development, Brundtland Report, extended the concept of sustainable development to non-renewable resources. Clearly, few mineral resources fit into the concept of sustainability as it was formulated 300 years ago for the management of forests, that the amount of wood cut should not exceed the growth rate. Such exceptions may be salt, magnesium, and potassium harvested from seawater. Most minerals and metals are non-renewable and their use should be managed according to the following rules. Consume as little as possible, optimize the recycling rate, and increase the efficiency of using natural resources, especially of energy. The original concepts of sustainability considered mainly the interests of latter generations. In the Geo Declaration, UN Conference on Environment and Development 1992, the concept of intra-generation fairness was added to allow for the interests of the living generation of mankind. In fact, the world's population's rapid growth and demand for a better life enforce a continuing expanse of raw material production. Yet, every individual extractive operation must have the acceptance of public opinion. To reach that aim, all stakeholders must profit, and the mine's social as well as natural environment need to be improved. The radical call that sustainability requires immediate termination of mineral exploitation is, of course, social and economic nonsense. Gilpin 2000, let us use needed resources in the interest of living humans and let us trust in technical and economic inventiveness to provide for later generations. The mining resources conundrum, but is there a sufficient mass of minerals for an ever increasing consumption? Because of the limited size of our planet, it is true that geological resources are principally finite, although very large indeed. The search for most minerals has hardly gone deeper than a few hundred meters below the surface, and only lands, shallow seas, and the margins of the vast oceans are fully explored for petroleum and gas deposits. Yet, even in the well-known Gulf of Mexico, the new giant Tiber oil field was recently 2009 discovered. Metal mining on the seafloor has a large future potential. Giant unconventional gas resources promise to fundamentally alter geopolitics of global energy supply. In contrast to reserves that can be exploited at present, economic and technological conditions are only a small part of the total geological endowment, because searching and refining reserves is a capital investment that must be paid back with interest. Due to the rules of depreciation for future income, reserves are typically defined for the next 10 to 30 years. The result is that at any time, a division of total reserves by the yearly consumption, the R by C ratio or life index will predict that in 10 or 20 or 30 years' time, the world will run out of the respective minerals. This fundamental error was famously made by the Club of Rome. The world will run out of the respective minerals. The world will run out of respective minerals. The world will run out of the respective minerals. This fundamental error was famously made by the Club of Rome when it was predicted this dire fate for the years 1990 to 2000 Meadows et al. However, predictions of impending catastrophes are always popular, and this gave Club of Rome's hypothesis a sweeping impact. Actually, the imminent scarcity of important minerals was announced many times in the past but never arrived. The term life index is misleading, and the figure is rather an indication of specific conditions that dictate financing, production, and marketing. Uh, is an indication of specific conditions that dictate financing, production, marketing of individual metals and minerals. With few exceptions, individual R by C ratios change little over time scales over several decades. In the future, just as in the past, science and technology will continue to provide mineral raw materials needed by society, both by finding new deposits and by providing natural or synthetic replacement. R by C life index. Temporary scarceness of critical raw materials is only possible if political constraints distort markets. European Commission 2010. Furthermore, exploiting lower grade ores, producing functional replacement for certain minerals and metals, and recycling of materials all need energy. And accordingly, energy is the most important natural resource of all. It is undeniable that there are physical limits to the availability of certain quality classes of raw materials. Severe problems arising from this fact are not expected as long as the unlimited resource of human creativity is here and the freedom to search for solutions. The continuously expanding reserve base for practically all minerals, roughly in parallel to increasing consumption, is the best proof of this principle in the mining industry. Okay, part one is the metalliferous ore deposits. Okay, economic geology defines ore as a natural material or rock, which from which minerals can be profitably extracted. Mining professionals use the word and in an identical connotation. Note that metals and minerals can also be recovered from quite exotic materials that are ore sensu stricto. For example, saline brines, lithium, magnesium, geothermal waters, zinc, metal accumulating plants, nickel, phyto mining. Okay, acid mine water, copper, and of course recycled scrap iron. So these are the places, the odd places from where again metals can be found. The term ore is also applied to metalliferous minerals in a rock. Okay, this is important. The term The term ore is also applied to the metalliferous minerals in a rock, for example, chromite in dunite or magnetite in gabbro, ore minerals. Okay, basically the ore minerals. Ore rock, commonly just called ore, is typically an intergrowth of useless minerals gang with ore minerals. Massive ore consists of ore minerals only, with little gang, for example, high-grade hematite iron ore. Ore deposits formed by geological process systems that can be viewed as a large cycle of constructive example magmatism and destructive sectors example weathering figure 1.3. Within this cycle of earth materials, individual metals have specific enrichment sites that depend on chemical and physical properties of the metal and or its compounds. It is very important to remember that biogeochemical fluxes mediated by life control many ore forming processes. Part 1 of this book is divided into two chapters. In chapter 1, general observations, characteristics and interpretations of ore deposit formation processes, process systems and associated outstanding deposit types are presented. In Chapter 2, the economic geology of metals is systematically presented and illustrated by reference to specific mining districts and deposits. Chapter 1, Geological Ore Formation Processes, Metallogenesis. So, energy flow from the Earth's interior and from the Sun drives geological process systems. The concentrations of ore and minerals is part of these systems, which comprise intrusive and extrusive magnetism, weathering, erosion, transport, and sedimentation, followed by diagenesis and metamorphism. In this chapter, we aim to acquire an overview of these systems in respect of the principles which govern the generation of ore deposits. Finally, the inspection of the different major systems is brought together in a synthetic view of global dynamics and metallurgy, that is, the science of ore deposit formation. This chapter lays the ground for the rest of the book. A. The science of ore deposit formation. For a long time in the past, processes associated with differentiation and cooling of magmatic bodies were thought to be the main agents of ore deposit formation. Starting with mafic melt, ore minerals can form upon cooling or metal-rich melts can segregate from the silicate liquid. Because mafic silicate minerals crystallize at higher temperature, immediate and intermediate and felsic residual melts are formed with their own suite of ore deposits. Late stage magmatic fluids collect metals and produce hydrothermal mineralization. Okay, so there are some scientists, Lindgren, Nigli, Schneiderhorn, Stanton, Gilbert and Park, and many others developed this concept of igneous ore formation in addition to the role of weathering, erosion, and sedimentation and concentrating metals was recognized. Metamorphic processes were seen to transform previously existing ore, but without appreciable mass transfer. More recently, these earlier views, here very simplified on ore deposit formations, were fundamentally expanded. Robb 2005, Evans 1998. First, the discovery of plate tectonics caused a revolution in understanding the dynamic interaction of the Earth's crust and mantle. Plate tectonics determine the origin and distribution of many ore deposits. Present ore forming processes were investigated. Outstanding impulses brought the exploration of ocean floor hydrothermal venting that produces metal concentrations, which closely resemble long known ore deposits, example copper in Cypress Island. The application of new technologies of the geosciences, example trace element analysis, microprobe isotope geochemistry, fluid inclusion investigations, mathematical modeling, and simulation. Guided by old and new hypotheses led to the changes in metallurgic thinking and to the recognition of additional ore formation systems. For example, one example is the dehydration of the sedimentary basins during diagenesis. Expelled fluids cause appreciable geochemical mass transport and formation of numerous metallic and mineral concentrations without the involvement of igneous processes. Furthermore, The role of dissolved salt, hydrocarbons, reefs, and cavities in diagenetic core formation was illuminated. Long after the first hypothetical consideration, metamorphism was finally proved to cause migration of aqueous fluids that transport and precipitate metals. The classification of ore deposits by major earth process systems is in principle quite simple. Complications arise mainly because of the extreme variability of individual deposits due to manifold combinations of different processes and factors. Therefore, some authors prefer to arrange deposits into associations and types which are related by geological setting, paragenesis, and form, but not necessarily of the same genetic process. So, therefore, some authors prefer to arrange deposits into associations and types. Okay, and related by geological setting, paragenesis, and form, but not necessarily by the same genetic process. Okay, other authors dispense with geological environments and concentrate mainly on processes. Other authors dispense with geological environments and concentrate mainly on processes, like Rob. In this book, fundamental geological cycles and ore forming systems are to guide the reader through metallurgy. So, different authors have approached the subject in different ways. The genetic term of table 1.1 provide the basic vocabulary of metallurgy. Okay, we will keep it till this much and continue in the next part.